Okay, so hi guys. There are experimental results where the classical physics cannot explain. That includes the block body radiation and the wave properties of electron. The formulation of Schrodinger equation enables us to analyze and explain the state of hydrogen atom, which started the analysis of atomic properties of different elements. Let's start the lecture. And this is the outline of this lecture. Let us start by introducing the Schrodinger wave equation, formed in three dimensions, expressed in spherical coordinates. You may pause this video if you want to explore this quite long equation. This can be solved for a hydrogen atom with a potential energy function as shown. So U is equal to negative ke squared over r. I will not show here the complete solution, but it has a form of psi, or the wave function is equal to this product of the radial and the two angular functions, theta and phi. The idea here is the separation of variables. That is the method in solving this quite complicated equation. Let the solutions be single valued, and the wave function approaches 0 as r approaches infinity. Each spatial coordinates or variables, so we have r, theta, and phi, generates a quantum number. In addition, we will have a spin variable that will act as the fourth quantum number. In the solution of the Schrodinger equation for hydrogen atom, the radial function exists for integral numbers 1, 2, 3, and so. This is called the principal quantum number n. We have obtained this expression for energy with the Bohr model, and the n variable here is the principal quantum number. One part of the solution for the Schrodinger equation is the polar function, or the theta. It shows the quantization of the electron's orbital angular momentum, as shown. The magnitude of the orbital angular momentum is expressed as this. So L, the magnitude of angular momentum, is equal to the square root of L times the quantity L plus 1 times this h bar, wherein L is our orbital quantum number with the value of 0, 1, 2 up to n minus 1, wherein n here refers to our principal quantum number. Note that in Bohr, we were able to get the value of the magnitude of the orbital angular momentum, which is equal to n times h bar. And these two equations are not the same. In the classical perspective, let us check the orbital angular momentum of a given particle here with mass m as it rotates in an elliptical orbit due to a force. The angular momentum vector L has a magnitude equal to mv times d, wherein d here refers to the perpendicular distance of this force with respect to this velocity vector here. We can also define the net torque on the particle, which is equal to the rate at which the angular momentum vector changes. The angular momentum L of a particle will have a constant magnitude and direction along the orbit, and the net torque, or the torque exerted, will be equal to 0. The angular momentum is conserved with the given force, while the L here, the vector of the angular momentum, vary from the ellipse. Now we can also get the relationship of the orbital angular momentum with the orbital magnetic dipole moment. Let us consider an electron moving in a circular path as shown. This will generate a current according to this equation, wherein E is the charge on electron and F is the frequency of rotation of that electron. Same with the Bohr magnet, we can define a magnetic dipole moment mu according to this moving electron with the magnitude equal to I times A, wherein I here is similar to this one, so this will be equal to EF times the area of our circle, and therefore we can define the magnitude of this orbital angular momentum. So this is equal to mvr. Then we can rewrite v here in terms of 2 pi r f, the frequency of the motion of the electron, and this will be equal to 2me times the magnitude of this, of your magnetic dipole moment. So therefore, we have this relationship between your magnetic dipole moment and orbital angular momentum. If the orbiting electron is placed in an external magnetic field, we can express a torque as the cross product of the magnetic dipole moment with the magnetic field. Therefore, we can also express this classical energy for our orbiting electron, which is equal to the constant E over 2m times L, the orbital angular momentum, times B, the applied external magnetic field. Zeeman effect refers to the splitting of the spectrum line into several components by the application of the external magnetic field. We will discuss this one later. After discussing the relationship of the orbital angular momentum with its orbital magnetic dipole moment, we now go to the third quantum number. The solution for the function phi generates the magnetic quantum number m sub L. This determines the z component of the orbital angular momentum. As we have defined previously, we have also the following relationship for our magnetic dipole moment and the orbital angular momentum. Let us now go back to the Zeeman effect. Assume that one electron atom is placed in an external magnetic field along the z direction. The direction of the orbital angular momentum will be oriented wherein its z component will be quantized in terms of the magnetic quantum number and the reduced Planck's constant. We'll talk about this later. The total energy is expressed as the sum of the energy E naught, and this refers to the energy before we introduce the magnetic field, and the energy EB, E sub B, which is due to the introduction of external magnetic field. The magnetic field split the sublevels into 2L plus 1 space, and it is proportional to the magnetic field B. The factor EH over 2m is called the Bohr magneton, as shown here. This is generally called the normal Zeeman effect. This type of splitting is observed with hydrogen and zinc singlet. This type of splitting is observed for spin zero states since the spin does not contribute to the angular momentum. Take note that the transitions between the states follow the selection rule, which does not allow a change of more than one unit of the quantum number m sub L, as shown here. So again, in a normal Zeeman effect, if an external magnetic field is introduced, sharp spectral lines, for example, for N3, principal quantum number 3, going to 2, shown here. So this is N3, this is N2. Split of multiple closely spaced lines are observed. Note that the transition follows the selection rule we have discussed previously. So these are the allowed transitions from n is equal to 3 going to n is equal to 2. Then the last allowed transition for this case. Let's start with a little bit of history. In 1925, Goudsmit and Uhlenbeck suggested that an electron has an intrinsic angular momentum called the spin. The intrinsic spin angular momentum S of the electron is observed in the deflection of beam in the Stern-Gerlach experiment. We can get the magnitude of the spin angular momentum, capital S, in terms of the spin magnetic quantum number, small s, shown here, wherein s, or small s, is equal to 1/2. This has a relationship with the z component of the spin angular momentum S sub Z. The orientation of S are the spin up for positive 1/2 and spin down for negative 1/2. The intrinsic magnetic moment and the intrinsic angular momentum is related by these quantities. GS, so this quantity here, is called the gyromagnetic ratio. This is the ratio of the magnetic momentum to its angular momentum. We have defined two angular momentum. First, the orbital angular momentum, and second is the spin angular momentum. The total angular momentum J is expressed as the vector sum of the orbital and spin angular momentum. Small letters is used to quantum numbers, or number of states of individual electrons, while capital letters is used for quantum numbers representing the atomic states. Last, the magnitude of the total angular momentum is expressed as shown here. So we have discussed the following quantum numbers. First is the principal quantum number, we have the orbital quantum number, we have the magnetic quantum number, and we have the spin quantum number. Note that for the principal quantum number, we can refer to them as these letters in terms of shell. So n is equal to 1 for the K shell, 2 for the L shell, and so. For the orbital quantum number, it is written as follows. So L is equal to 0, that refers to S. Then P for L is equal to 1, and so. The wave function for N is equal to 1 and L is equal to 0 state, or the S state, is this radial function shown here, wherein A naught is the Bohr radius. The probability of finding the electron in spherical shell between R and R plus dr is this, refers to this equation. Thus, this is the radial probability density for finding an electron for the state n is equal to 1 and L is equal to 0. On the other hand, this is the wave function and the radial probability density for the excited state n is equal to 2, L is equal to 0. So we will not show the solution here. The probability of finding the electron is plotted at the figure here at the right. This shows that electron is not really moving in specific orbit, but in some sort of cloud of probability, as described by a probability density. The peak for, let's say, this one, so for the state 1s, is at the Bohr radius a naught, so somewhere here, while for the 2s state, shown below here, is around 5 times the Bohr radius a naught. There is an overlap with the probability of both states as well. According to Pauli Exclusion principle, no two electrons in an atom can have the same four quantum numbers n, L, m sub L, and m sub S. Let's check this illustration here. The first column of the illustration shows that two electrons in the ground state, we have spin up and spin down, do not have the same set of quantum numbers. Next, what if we have the third electron? The third electron is not allowed to occupy n is equal to 1 state. Thus, it must go to a different energy level. For this case, n is equal to 2. Last, let's check the third column. It shows an excited state where when an electron do not occupy the lowest available energy levels. It is possible to emit photons, in this case, when the excited electron here goes to a ground state. Let us now go to the periodic table. The electron configuration of an atom mainly describes the orbitals or the quantum states occupied by electrons on the atom. This shows that the quantum mechanics explains the gross features of the periodic system as shown here in the periodic table. This subshell label here is related to the quantum numbers we have discussed previously. Hi, if you have learned something in this video and you like my content, please consider subscribing my YouTube channel, JP Academia. See you in the next video.